even see you there. Notice how my books just fell? That's because of something called gravity.
Did you know that acceleration due to gravity is independent of mass? Well, it is. But what does that mean? Let's say you have an object of mass of 1 pound and a second object with the mass of 1,000 pounds. Theoretically, they will fall and hit the surface of the Earth at the exact same time. Specifically, when two objects fall, they are both affected by the same gravity, meaning they will both fall at the exact same rate and hit the ground at the same time. They both fall at the exact same time because acceleration due to gravity is a constant, g, that depends only on the mass of the gravitational object and the distance from it. This idea was determined by Galileo Galilei. In the 17th century, Galileo Galilei was an Italian astronomer, mathematician, philosopher, professor, and physicist. He was mostly known for his impact in the physics world. In 1604, Galileo constructed a hydrostatic balance for measuring small objects. That same year, he also refined his theories on motion and falling objects, then developed the universal law for acceleration, which all objects in the universe obey. The law of acceleration is made up of several components. However, the statement that is directly applicable to this topic is that all objects fall to the surface of the Earth at a constant acceleration, which brings us back to acceleration due to gravity. If acceleration is constant, why do
different objects fall at different rates?
Air resistance? An object falling on Earth hits an extremely large quantity of air particles, such as oxygen and nitrogen, which significantly slows down the falling object. Objects that have a greater surface area hit into more air particles and therefore are slower than a more dense object with the same mass. Okay, so you may understand theoretically why gravitational acceleration is independent of mass, but you need mathematical proof. Don't worry, I got you. Force can be represented by F equals ma, which is the mass multiplied by the acceleration, and the force of gravity is represented by F equals mg, the mass multiplied by the gravitational constant g, which is equal to 9.8 meters per second squared. Fg equals ma, therefore mg equals ma. Divide both sides by the mass, then g equals a, therefore demonstrating that the mass cancels out and has no effect on the gravitational acceleration.
Okay, so I have a tennis ball and a lacrosse ball. They're both roughly around the same volume, so air resistance should be negligible, but have very different masses. The tennis ball is extremely light, whereas the lacrosse ball, not so much. When they drop, they're pretty much going to stay together. Now let's see.
The aim of this experiment is to show that acceleration due to gravity is independent of mass. While conducting this experiment, we will need to consider several design considerations. The height must be tall enough to show the difference, if there were to be one. The objects need to be different masses. The volume should be around the same in order to avoid noticeable difference because of air resistance. Doing this experiment inside would allow for less influence from outside interferences, for example, wind or the weather. A bonus would be to try the experiment with several different objects. Method: grab two objects, determine their masses, find a platform to stand on, hold the two balls at the exact same height, use landmark references in order to do so. Drop balls, start timer 1 and timer 2, both at the same time. Do over, change balls, switch hands in order to have the most even results. We did the experiment with two different types of balls, tennis balls and lacrosse balls. The lacrosse ball had a mass of 156 grams, whereas the tennis ball had a mass of 58.5 grams. In the first experiment, starting from a height of 2.2 meters, the time of the lacrosse ball was 0.23 seconds, whereas the lacrosse ball was 0.25 seconds. The difference was noticeable. In the second experiment, the height was from 2.4 meters. The tennis ball hit the ground at roughly 0.277 seconds, whereas the lacrosse ball hit the ground at 0.273 seconds. The difference wasn't very noticeable, and it was hard to measure. Third experiment, the height was from 2.4 meters. The time of the tennis ball was 0.281 seconds, and the lacrosse ball was 0.76 seconds, and the difference was more noticeable. So I went to the gym and got a 5-pound weight and a 25-pound weight. They had different volumes, however, the 5-pound weight was more dense,
so air resistance wouldn't have been as prevalent. I conducted an experiment once, however got yelled at the gym for dropping weights and also was very embarrassed to film it, so here we are. My friend Sam and I observed that the 5-pound weight took 1.23 seconds to drop, whereas the 25-pound weight took 0.098 seconds to drop. Based on the surface area and volume, I assumed that air resistance would have been stronger in the 25-pound weight. However, these results show that it's only an error analysis and not to do with the mass. Had mass been a part of the acceleration, the 25-pound weight should have gone down a lot faster. Time for discussion. As you probably noticed, we did not get one prominent result come out of the experiment. So a reminder, in the first experiment, the tennis ball landed first. In the second, it was the same time, roughly. And in the third, the lacrosse ball hit the ground first. So if the experiment had went perfectly every time, they would have hit the ground at the exact same time. This means that there were some outside influences affecting it, or just airs in general. So first, let's talk about air resistance. Although the balls had extremely similar volumes, they still had a different volume, and the tennis ball was actually made out of a yellow fluffy wool material, whereas the lacrosse ball is kind of like a rubber, meaning the tennis ball will actually have more surface to it, just in the particles of air will react with more of the tennis ball rather than the lacrosse ball. So in the situation where the tennis ball landed after the lacrosse ball, that was most likely the reason why. It's also hard to completely control the reaction time. So with your right and left hand, your right hand might drop the ball faster than your left hand. And so even though we did several different experiments, I only recorded the 3. It's hard to have your hands drop the balls at the exact same time, and also on the other end. So when one person is timing and the other person's timing the other ball, when they press stop, once the ball hits the ground, who's to say whose reaction time is faster? So that's where the errors may come into play. The relationship to this theory, however, is that it did show both ends of the experiment. So on average, they landed at the same time, and not showing that, and specifically showing that not just one mass dictated it. So the heavier one didn't hit the ground first, so, and the lighter one didn't always hit the ground first either, so mass didn't really have that much to do with it. And how to improve that lab specifically would, 1, get rid of air resistance, so go to a vacuum. Hit up NASA, even though it's expensive, ask them, hey, let me use your vacuum. It'd be cooler to see it with a bowling ball and a feather, which has actually already been done. And also having the exact same volume, so if you happen to not have a vacuum at your disposal, you use the exact same volume, and just denser objects, then it could show a more accurate representation of what no air resistance would mean. Also, having a machine that would drop the balls at the exact same time would be helpful as well. And sensors for the timing, so as soon as the machine would open and have the balls fall, they would hit a time sensor like the ones that they have at swimming pools. They're very expensive as well, so if you're looking to prove it yourself, gotta give up the big bucks. So in conclusion, mass is an independent variable from acceleration due to gravity. When something's accelerating, no matter what mass it is, it's going down at 9.8 meters per second on Earth. And even on other planets, it's gravitational constant g. So in conclusion, I think that this experiment was successful. Thank you for watching. I hope you enjoyed learning with me. I enjoyed learning with you.